Hello, this lecture is about matrix inverses and non-singular matrices. So the first theorem that we learn here says that we assume we have two matrices of with the same number of rows and columns. They are both square matrices. And then we note that the implication of this theorem is that their product, their multiplication, is non-singular if and only if each of them is also a non-singular matrix. So it is a powerful theorem because it's double directional. As it has an if the product is non-singular, then each matrix is non-singular, and the other direction, if you assume that each matrix is non-singular, therefore the product will also be non-singular. Then the next theorem that we learn um, tells us the following. If we have two square matrices, again, the same dimensions, same number of rows and columns, then if the product of these two is equal to the identity, it suffices with knowing one side of, it suffices with either knowing that multiplying on the right of one matrix is equal to the identity, or multiplying to the left of one matrix is equal to the identity. Because once that is true, then we have the following implication. So if we know that the product A times B, in other words, multiplying B on the right side of A is equal to the identity, that implies that B is what we would call the inverse of A. On the other hand, if we have that B times A equals the identity, then that would imply that A equals the inverse, the inverse of B, right? So having information on one side of this multiplication, multiplying by the right side or the left side, it immediately implies that the other product on the other side is true. Okay, so uh, as I said, AB equals I implies B is the inverse of A, and that in turn implies that the product B times A, this product will be equal to A inverse times A, which is I, right? And so that's easy to see how this implication here is therefore obtained. And invertibility and non-singularity. So remember the definition of singular matrix has to do with the null space of a matrix being a space that contains only the trivial vector, the vector of zeros. And so if a matrix has that type of null space, it's considered non-singular, but there's also a connection with the non-singular matrix having an inverse. And so we say, suppose we have a square matrix, then that matrix is non-singular if and only if the matrix is invertible. So in other words, the null space of A contains only the trivial vector, the vector of zeros, if and only if we say that there exists the so-called A inverse, right, which is what we denote with these symbols. Okay, and so here we have the theorem with all the equivalent statements, and this theorem tells us, suppose we have a square matrix with n rows and n columns, then all of the following statements are going to be true. So some of these statements we are familiar with, right? So we have this means that each of these 6 statements, each of them implies the other 5, right? So if 1, then 1 implies 2, 1 implies 3, 1 implies 4, and so on. So each of them implies all the other ones. If the matrix is non-singular, then so you can see that we just stated previously it was a connection between 1 and 6, but 1 also implies 2, 3, 4, and 5, right? So non-singular means that the null space contains only the 0 vector, If the matrix is the matrix of coefficients of a linear system with a vector of constant speed, then that linear system has a unique solution for each uh, choice of the vector of constants. And invertibility, very importantly, now this type of null space, non-singularity, invertibility, now this is connected to the definition. This is connected to linear independence. So the columns of an invertible matrix are linearly independent. The columns of a non-singular matrix are linearly independent. And the columns of a matrix of coefficients um, or in a system with unique solution, so this case, a system with unique solution, the columns of the matrix of coefficients are also linearly independent. So we now introduce a definition which is in a similar spirit to some of these theorems we were first talking about initially. So one of those theorems said something about multiplying a matrix. If you know that A times B equals I, then B times A is also going to be equal to the identity. The important thing is this ability to multiply by a matrix and then that product being equal to the identity. Okay, uh, again, this goes really back to case the core here is whenever you multiply a matrix times its inverse, that's actually the definition of being an inverse. A times A inverse equals the identity. A inverse um, times A is also equal to the identity. So for the because of the definition of inverse of a matrix, in fact, that product is commutative, right? The product of the matrix times its inverse is a commutative. It satisfies the commutativity property. But for matrices that have non-zero imaginary parts, that have entries with real parts and imaginary parts, we would say that now we consider the product of the adjoint of a matrix times itself, and if that product equals the identity matrix, then we're going to say that the matrix is going to have a name, which that name is called unitary. So the fact that the adjoint times the matrix equals the identity, the fact that that is the definition, this also implies that the adjoint is indeed the inverse of the matrix. Okay, and the matrix is also the inverse of the adjoint of the matrix. Okay, so that's a lot of things here on that definition. And here we have an illustration with a matrix. This matrix that we have in this illustration is a 3 by 3 matrix, and it is an example of matrix that is unitary. I'm not going to do these computations here by hand. You will have to compute the adjoint, then you have to compute the product adjoint times u, and then you have to compute u times the adjoint. Okay, and then you will verify that this product equals the identity and this product is also equal to the identity. When we say identity, we mean this matrix, the matrix that has 0, 1, 0, 0, 0, 1, 1, and 0, 0, 1. Right. So each of these two products equals to that identity. And one thing to say here to mention is that, by the way, this verification of verifying that u in this example is unitary is left to you as an exercise. Okay, so you are left with a task here of carrying out these computations as an exercise. So this product, this 3 by 3 by 3 by 3 matrix, is left to you as an exercise, this verification. And lastly, but not least, we notice that if we have a matrix that has n columns, that we're going to establish that this matrix is unitary if and only if the columns of this matrix define a set that is both orthogonal and the norm of each of these columns is equal to 1. Okay, so that's what is known as an orthonormal set. And part of this is a powerful theorem because, as we may notice, right, here there is a powerful statement. It is an if and only if statement. So if the columns are orthogonal and each of the columns has norm equal to 1, then the matrix would be unitary. If the matrix is unitary, then that set, the set of all the columns, is considered an orthonormal set. And part of the proof of this theorem is going to rely on taking a look at this matrix, the adjoint times itself. We take a look at the ith jth column of that matrix. Remember that one way of looking at matrix multiplication is by looking at the ith column. Okay, this is the ith row, excuse me, multiplying the j column. And so if you look at that product, this is something that it's another theorem. Then we're going to see step by step here. What is the ijth entry of a adjoint times a? And then applying different ways of looking. So the ik entry of the a adjoint is the transpose of the complex of that matrix on the ikth entry, and the ith k of the transpose is precisely the ki of the adjoint. So this is the transpose, excuse me, this is the transpose of the complex conjugate, and that means that that would be the ki entry. That would be the ki entry of the complex conjugate. So that's simply applying the definition of transpose, and therefore this is interpreted as the conjugate of the ki entry of the matrix I. And so there we have the conjugate. We can understand this as the kth entry of the conjugate of the ith column. Okay, and similarly we can interpret this term as the kth entry of the column j. So in this form we invoke the definition of inner product. So the inner product between the ith column and the jth column is going to be equal to 0 or 1. And this is now, instead of doing this in one-sided, the set is orthogonal, the set of columns orthogonal, if and only if this inner product is 0, 1, and we saw how these definitions are going to be connected to the ijth definition of the ijth entry. And that is consistent there, and therefore it's not difficult to make the conclusion with the sequence of if and only if statements that orthonormality has to do with the property of being a unitary matrix. Okay, and so we conclude this lecture pointing that in this example we can verify the previous theorem still using this matrix, right? So there's left as an exercise to verify that first this matrix is unitary, and then we can use this as an illustration of this theorem which establishes that this set of the columns of this matrix is indeed an orthonormal set.